So in this problem we got, this is my child on the snow, and that's the rope that he's holding on to. Okay? Guys, I'm doing video. All right. And we're told the angle of elevation, so he's just sitting there. It doesn't make that explicitly clear in the problem. I have a gripe about that, but the kid is holding himself. Obviously, if he lets go, he's going to slide down. If you've ever been skiing or snowboarding, you know that it happens real fast. It doesn't take that steep of a hill to go pretty fast. So anyway, we're told the angle of the hill, and we're told the weight. We're not told the mass, we're told the weight. So since we're told the weight of the kid is 81 newtons, for me it's 81 newtons, then that's mg. So I don't plug that in for m, I plug that in for mg. And my angle is 31 degrees. Everyone's numbers will be different there. And then we're told to find the force on the rope by m, which is the kid, right? This is a weird thing though. When we draw a free body diagram for the kid, we draw the forces that are acting on the kid. But we're asked to find the force on the rope by the kid. So this is my picture of a hand. This is my picture of a hand. And then this is the rope that the kid's holding on to. Okay? The kid's holding on to the rope. He's pulling on it, right? And the rope's pulling on him. Newton's third law says that those two forces are the same. So even though it says find the force on the rope by m, remember that Newton's third law, so by Newton's third law, we also know that this force, this question could have said find the force on m by the rope, right? Newton's third law says those are the same. I push on the table pushes on my hand. I hit the table hits my hand and it hurts. I pull on the rope pulls on me. It's that if you ever climbed a rope or used a rope to help you climb, that's the force that gets you up. It's the tension in the rope acting on you. And then your muscles, the tension in your muscles and how they interact with your bodies and all that. And then that transfers to your body. But you pull down on a rope to climb up. Newton's third law says the rope then pulls up on you, right? So anyway, the question could have said this and it's asking the same thing. So we're just asked to find the tension, essentially, that's acting on the child. Okay. So do my 5-step process here. By the way, I don't think of it as a 5-step process. I've just solved enough problems to where I just know that I draw a free body diagram, and then I make sure I know what coordinate system I'm using, and then I apply Newton's laws. And I vector decomposition if I need to. Then I apply Newton's laws based on whether it's accelerating or not, and then I just solve the equations. Remember in step 4, that's when we generate the equations. Okay. All right, so step 1, free body diagram. When we're on a ramp, I like kind of making a dotted line showing the orientation of the ramp on my free body diagram. It will help, as you'll see in our vector decomposition, if we have to do it. So what forces are acting on the kid here? The first one's name the first one that comes to mind. Gravity. The gravitational force, which I know I can put F sub g, but I can also just label it as mg. A little too long. What other force? What's it? What's that? Tension force. And that's going to point along the string, right? Like we showed, like you and I showed weeks ago, way before I even got sick. I think that was before I got sick. So that'll be my tension force. There's one more. If this, let's do a little aside here. If these were the only forces, would this object be accelerating? Oh yeah. These forces are not going to cancel each other out. So it's going to be accelerating. Right? Remember when we add vectors, we line them up tip to tail? So the net force vector would actually point this way. So if these were the only forces, the kid would be accelerating down into the ramp like that, which obviously that's not happening. So that means we're missing a force. What force is that? What? Normal force. And it's called normal because it's opposite of weird, right? You remember why, right? A normal is a mathematically defined object. It is a ray or a vector starting on the surface, pointing away from the surface. So a normal force is a force that has that type of orientation. All right, there's my free body diagram. What if I add up all these forces? What do I get? If the kid's just sitting there. What? 0. Good. If I wanted a graphical depiction of that, if I want to add these vectors up, I try to do my best here. But when I do graphical or visual vector addition, I line them up tip to tail, all of them. So I have normal force, I have mg, and then I have the tension force. If the net force is 0, that always happens. Because when you draw your resultant, you draw it from the tail of the first to the tip of the last. Well, that vector has 0 sides. So this object is not going to accelerate because the net force is 0. Now, to truly analyze that, we got to break it into the x and y components, and we got to do all that stuff too. But visually and conceptually, you can kind of understand what's going on from your free body diagrams without even getting to vector decomposition. Okay. If, and this is key, that most of the time, 95% of the time, we use the standard coordinate axes. This is one case where we wouldn't want to. And let me ask you, let's see if you can see why. If I use my standard coordinate axes here, remember why we do vector decomposition. How many vectors would I have to decompose? 2. I'd have to decompose these 2 guys because they're not in line with my x and y directions. I wouldn't have to decompose mg, but I would have to decompose these 2 guys. Okay. So what we do is tip our coordinate axes. We're allowed to do that. Coordinate systems are completely arbitrary. It doesn't matter where you put them. As long as you're consistent with your measurements within them, it doesn't matter. And so I'm going to take my coordinate system, and I like pointing it down the ramp, the x direction, and then the y direction will be perpendicular to that. Remember, you can pick whatever coordinate system you want, but you want to pick the one that requires the least amount of work. Right? I don't want to do 2 vector decompositions. That's going to get gross up there. Right? I'm going to have to do at least 1, but if I can just do 1, I want to just do 1. Right? Okay. Now, with that in mind, you might want to put a little dotted line also, because now that we can see this first dotted line represents essentially the x-axis. This dotted line would represent the y-axis. So that's why I don't need to decompose the normal force or the tension force within this particular coordinate system. Which one do I have to decompose though? Force of gravity. And so to decompose force of gravity, all I do is draw my right triangle, right? And you can draw it this way. I've always been in the habit, because this is the way I was taught, of drawing my components this way, drawing my right triangle like this. I know it's weird at first because it's like skewed to the side, but just remember, these are our axes directions. Those are the directions that the legs of our right triangle need to be oriented with. So that's my 90-degree angle right there. And this is the angle that we're going to know. Okay? That angle is congruent to the angle of elevation of the ramp. Always. That's something you probably just want to commit to memory. Otherwise, you got to do this every time. I got that. I got this. How do I do this again? This angle is this guy's complementary angle. Call that beta. Right? This angle is 90 degrees. So this angle has to be beta's complementary angle. So that angle has to be theta. Or you can just, because you don't like geometry, especially geometry proofs, because I don't like geometry proofs, you can just remember that every time you have a ramp, and you're going to see this. If you take more physics classes after this one, you're going to see ramps and objects on ramps. It's just one of the things that you do in introductory physics classes. When you see that, just remember that when you decompose mg, what you're always going to, when you have a ramp, tip your coordinate axes with the ramp. Just do it. Do it. And so in that case, you're always going to decompose mg, and this angle will always be congruent to whatever angle the ramp is. Okay. All right. And that, when I decompose the vector now, this is the opposite component. So as we hopefully know now, it's the actual vector mg. It's the opposite component, so it's the sine component. This guy is the adjacent component, so it is the cosine component. And I like thinking of it this way. Once you decompose a vector, you're done with that vector. It doesn't align with your axes. That's why we do vector decomposition. We don't want to worry about it. So we can just completely ignore that actual weight force for the rest of the problem. Right? This is why we do vector decomposition, so that we can avoid that particular vector. And then I apply Newton's laws. Newton's first law or second law apply? First law. The acceleration of the kid is 0, so the net force must be 0, which we already discussed. How many equations can I generate regarding these forces? 2. One in the x direction and one in the y direction. Good. So I'm going to go ahead and do the net force in the x direction first, and I know it equals 0 because I know there's no acceleration here. Notice I don't need sigma F1 in the x direction because I only got one object. If I only got one object, I only got to do one free body diagram. But I can still get 2 equations, though, because I can still do the x and y direction. Then I'm going to unpack sigma Fx, which just means list the forces in the x direction, like we talked about yesterday. The forces in the x direction, let me circle them, are Ft is obviously in the x direction because we see it along the x-axis, but mg sine theta is also in the x direction. What can I say about those 2 vectors? They sum to 0, right? Which means their magnitudes must be the same. Good. So anyway, I have a positive mg sine theta. So I'm just going to list the forces, but with a negative if they're negative, if positive if they're positive. That one's positive. And then I have a negative tension force. The equations can get a little gross looking, but if you just follow the steps, it just leads. Everything leads to the next part. Don't make it more complicated than it needs to be. Yeah, this looks kind of nasty, but it's not too bad. We're asked to find the tension force. Can I find the tension force here? Do I have to look in the y direction? This is something you want to think about as you're going through solutions because it will dictate how much work you're going to have to do. Like, is this equation enough, given the information I know, to calculate the tension force, which is what I'm looking for? Yeah. What do I need? I need mg. I have mg. It's 81. I need the angle, 31 degrees. That's all I need to calculate the tension force according to that equation. So I just add the tension force to both sides. And then I like putting what I solve for on the left, so I have the tension force is now equal to mg sine theta. It's that simple. This whole thing led to, it's not much work here. Most of the work is in the free body diagram. That's why students that neglect the free body diagram end up actually taking more time. And not only that, they end up making a lot more mistakes, especially with the negatives. And so if you're neglecting this, you're probably not doing too well. It's almost a statistical certainty. If you just poo-poo the free body diagrams, you're not going to do well in this particular unit, which again is the foundation of pretty much everything we study this year. All right, and for me, I would just plug in the values, right? This is just going to be 81 times the sine of 31. Logan, you can do it in your head, right? What is that? I'm just kidding. I have a calculator. Oh, it's right here. I got it.
Do we do in degree or radian for our calculator?
I don't know. What do you think?
Degree.
Degrees. This is a good point. This is a good point, actually, because a lot of you are in pre-cal. Some of you are in calculus, maybe. In pre-cal and calculus, you're in radian mode when you're doing your trig stuff for the majority of the time. When you're in physics, pre-AP physics, we will always be in degrees. Always. Okay. Physics C next year we'll do radians. Radians are more better. Radians are nicer. Oh, this is on video. Radians are better. They're more elegant, more mathematically elegant. But degrees are what we're used to. And it doesn't involve pi, an irrational number. So, all right. Oh, safe. I told you. Save the questions till after the video. Gosh. Now you've been called out on the video too.
I know, I've been exposed.
I have 41.7. I got 41.7. Yours will obviously be different, right?
Yes.
Okay. That's the end of the video. Hit the like button. This is going on my YouTube channel. It's a lot of subscribers on my YouTube channel.
Oh yeah, I bet.
Check my MySpace page.